One of the most famous German icons is the Autobahn. And one of the most sacred values in the Autobahn is the concept of flow. God forbids if you restrict that flow. God forbids if you drive on the left lane at a slow speed, because in that moment you become what we call a bottleneck. This module, ladies and gentlemen, is about that. Module 6 is about constraint management, or the management of bottlenecks. And we're going to analyze that from the perspective of systems or processes. Okay, so what you will learn is, first, to learn how to define a process constraint. Second, to identify within a system where the bottleneck is located. And number 3, to determine, to calculate the capacity of a process based on that bottleneck. So these are the 3 goals. Okay, so what is a constraint? Any factor that limits the performance of a system and restricts its output. In other words, consider this picture in which every element that you see here, that means the animals, the cars, is what we can call the system. And all these elements are moving forward. Even though they look like these guys here that are moving in the opposite direction, they're all moving forward. And the question is, what is going to be the speed of this whole system? Is it going to be the speed of this very fast Lamborghini Gallardo? I don't know if that is that car. No. In fact, it doesn't matter if that is a Lamborghini, if that is a Fiat 500 or whatever car you have. The speed of the system is going to be defined by the slowest animal in this picture. That's it. That is a sad story. So, bottleneck is any restriction of flow. As you can see in this bottle, it restricts this flow, and it can come in different forms on any process. For example, at the office, picture this is an office in which information is flowing in the form of papers or documents to be processed. And here, clearly, you notice something strange, and that is this accumulation of papers. This is inventory, right? And the reason why it gets stuck is because this step in particular is slow. Actually, is the slowest from the whole system. That means everybody's working very fast, very hard, but at the end it doesn't really matter because documents will be stopped here. You see? So the speed of this whole flow is defined by this desk. Yeah? So this could be a process, for example, for you getting a driving license, for instance, in which a lot of people are involved, perhaps. You might also have another system coming back to the highway. Here, clearly, you also see the bottleneck, and you also see this accumulation of cars. This is basically inventory. It's the same. It's WIP, and that is WIP as well. Okay, so you see the effects of the bottleneck. So let us have a look with this animation. What kind of effects they create? So picture the following. You have a system that consists of 5 different workstations that work at 5 different speeds or rates of production. For example, workstation A works at a rate of 30 units per hour, whereas B at 20 units per hour, 12 units per hour, 60 and 15. You can see the manifestation of that speed on this picture. So you see how the 12 is going very slow, and then they pass the ball, and D goes super fast. So the whole system is on balance, so to say. And the question is, what is the effect of this bottleneck to the complete system? And the effect is going to be the speed of the complete assembly line or chain that you see here. In other words, this process will run no faster than 12 units an hour. It's not the average of all these, no, it's always the slowest, and the slowest defines the speed of the whole. That means it doesn't matter if you have a Lamborghini, if you have a Ferrari, or if you have, I don't know, a BMW. If at the end you have a Fiat 500, that's the one that defines the speed of the whole chain. And therefore, we need to identify it in order to exploit it and to improve it, because by improving the bottleneck, we can improve the complete system. You see, this is how we focus our efforts and attention. So the bottom line is the system cycle time will be determined, governed by the bottleneck. Okay, so you have many examples also in nature. This is just a picture I once received on Facebook. And here you can read it. This is basically a copy paste from attached to the picture. But the whole idea is the following. You have a pack of wolves, and some wolves are very strong and fit, and some are weak and slow. And you want to keep the pack together. So what are you going to do? Will you place the strong and fast on the front or on the back? And what will be the consequences? If you put the fast wolves on the front, they will depart from the rest. So what you have to do is actually the opposite. You always have to subordinate the whole system. It doesn't matter how fast they can go, they will go as fast as the slowest wolves. So by the way, these are the slowest wolves, ready to be sacrificed, by the way. And back there is the leader. The leader stays on the back in order to control the chain, the system. So here is already a very interesting lesson from nature, how the wolves organize themselves. So the pack moves according to the elders, which are this. Okay, so this concept of known as theory of constraints is coming actually from this individual that you see here. His name is Eliyahu M. Goldratt. He just passed away, I think, recently, like 3 years ago. He wrote a book, and this book, I never get tired in recommending this book. And honestly, guys, you should buy it and read it. Do yourself a favor. This is not a textbook. This is a book written as a novel. And the target group for these books are business people, business managers. It's so friendly written. There is a whole drama in this book with characters and stories. So, but in this book, when you read it, you will understand the full concept of the theory of constraints, which is a systematic management approach. It's a method with steps that focuses on actively managing those constraints, bottlenecks, that impede a firm's progress towards its goal. And by the way, here's a spoiler, sorry for that. The goal for the firm is to make money. That's the reason why this book is called The Goal. And money in this book, in this perspective, is measured as throughput, as a flow, the rate of money that enters to the company. So every effort that you are doing in improving a company should be in favor of improving that money flow that enters to the company. It's not about increasing efficiencies. It's not about optimizing isolated elements. It's about optimizing the complete system, and you do that by identifying the bottleneck. It's really worthwhile. Check it on YouTube. I think there used to be even a movie, so why not? Go for it. Okay, so theory of constraints is a problem-solving methodology, and it focuses on the weakest link in a chain of processes because, as they say or they claim, the strength of any chain, it is defined by its weakest link. Think about it. You have a chain composed of iron links, and maybe one of these links is just made out of paper. You pull that chain, and what's going to happen? It's going to break. And where? I guess you know where the paper is. So the weakest link defines everything, the weakness of the company. So the constraint is the slowest process. Flow rate through the system cannot increase unless the rate at the constraint increases, as we have seen in that animation that I previously showed you. So for example, picture the following. Imagine that the flow of goods is represented by this pipeline, and the bottleneck is represented as a physical bottleneck here. So we have workstations working at different speeds, and always the slowest, which in this case is number 2, is going to define the exit rate, just like what we have seen. So this is the same concept, nothing new. And the whole idea is how can we expand this bottleneck so that we can reach or we can balance it to the rest. Now, in this particular example, we were able to expand it from 50 to 200, right? But sometimes it's not possible. Sometimes you can only go as far as, let's say, 100 or 150. So what is going to happen then? Then you're going to subordinate the rest of the system to that speed. In other words, you don't want to run faster than the bottleneck. It's kind of counterintuitive, right? Because if you have equipment that can run very fast, why not running very fast? Why not exploiting the economies of scale and making tons of parts and processing things? That's good. But if at the end you cannot go as fast as the bottleneck, by doing that, by running the other elements fast, you create more harm than helping, right? You're producing more than what is needed. Okay, so theory of constraints is a methodology, and it consists of 5 steps, which are the ones you see here. Number 1, you need to identify the system's bottleneck. So so you have a chain, identify the chain, and then which one is the slowest. Number 2 is about exploiting the bottleneck. This is the terminology, exploit. Number 3, subordinate, elevate, and repeat. So I'm going to explain more precisely. Number 1, identify. That means find the process that limits the effectiveness of the system. Here, station number 2, clearly. Number 2, improve the rate of the constraining process. So what does that mean, improving? I don't know, make it faster. How can we make this thing faster? Well, we can increase its capacity. Maybe we have only one person doing a job. Why not getting another person? So now we have 2 persons, and suddenly we increase from 50 to 100. That is increasing its capacity. This is called exploiting. You can also, here we have a Japanese word, kaizen means continuous improvement. It means how can we find ways to improve this little step. So sometimes you can tweak here and there and you can speed up the process. Number 3 means subordinate. That means you have to adjust the rates of the other processes in the chain to match that of the constraining process. That means if you go, I don't know, to the forest with 4 of your friends and you want to keep up, you want to stay all together, that guy who is the slowest, for whatever reason, you place that person on the front. And so that everybody is subordinated to the speed of that person. If that person needs to make a break, everybody makes a break. That's it. Because if you do it in the opposite way, you're going to lose them all, right? If you put the fastest on the front, that guy is going to be very far away, and the slowest is going to be lost in the woods. So subordinating means the rest of the system runs at the speed of the bottleneck, and you want that bottleneck runs as fast as possible. That's why you are exploiting it. Number 4, elevate the system rates. If the system rate needs further improvement, the constraining process may require extensive revision or elevation. That means if we improve workstation 2 from 50 to 100 and we subordinate 1 and 3 to 100, then we have to find ways as to increase further in approximating the 200 that at least 1 and 3 can run. That's what it means, elevating the whole system. And number 5 is a cycle, is repeating. If these steps have improved the process to the point where it is no longer the constraint, the system rate can be further improved by repeating these steps with a new constraint. Okay, so here's a hint. Picture a factory that can produce, 100 units an hour. Yeah, but maybe the constraint is no longer inside of the factory. The constraint might be outside of the factory, might be the sales department who cannot manage to create a demand rate of 100 units per hour. So if the demand rate is only 80 units per hour, the rest of the factory is going to be subordinated to that constraint. You see, just like in the just-in-time that we talk in Module 7. So that is the whole idea. So there is always a bottleneck. You just have to look for it. Sometimes it's outside the system. So let us apply the concept of theory of constraints to this example, which is, by the way, a bank. And in this bank, they are processing customers' loans, right? So here we have a flow chart with steps and also with times. The numbers that you see here in parentheses represents the time needed per loan to perform that specific activity. So for instance, for checking loan documents and put them in an order, they take on average 15 minutes per loan. To categorize them, 20 minutes per loan, and so on. So here is an explanation of the whole process. So number 1, first, approved loans applications first arrive at activity or step 1, where they are checked for completeness and put in order. So that's this box. Where's the cursor? Here. That's this box. Number 2, at step 2, the loans are categorized into different classes according to the loan amount and whether they are being requested for personal or commercial reasons. So they either go here or here. Number 3, while credit checking commences at step 3, loan application data are entered in parallel into the information system for record keeping purposes. That's here. And lastly, number 4, all paperwork for setting up the new loan is finished at step 5. So these are all the steps. And here we have loans, documents flowing. Okay, so the 3 questions that we have to answer is, first, which single step is the bottleneck? So identification of the bottleneck. Number 2, what is the lead time for a customer's loans to flow the complete system? That means for a loan to go from the starting point until the last ending point or step. Number 3, what is the maximum number of approved loans the system can process in a 5-hour work day? So in order to answer this is about the capacity of the system. How many customers per hour can we serve? How many loans per hour? Okay, so let us start with the first question. Which single step is the bottleneck? Have a look at the flow chart. So what do you think? Remember what I just told you. That is right. So you have all these 5 steps and the bottleneck is number 2, the step 2, because that is the slowest step in the whole system. And if you remember well, that is going to define the speed for the whole system and hence the capacity for the system, how many loans we can process by a given time. Okay, so number step 2 is bottleneck. Second question. What is the lead time for a customer's loan to flow the complete system? So from the starting point to the last, what do you think? It takes 15 minutes, it takes 20 minutes, and then here we have something in parallel, but what is going to be defining the speed? The slowest. So that means 15 and 10 minutes. So in other words, 15 plus 20 plus the maximum value of these 2, which is 15, plus 10, that means 60 minutes on average. So it takes roughly an hour for a loan to flow through the pipeline, through the system. Okay, so that is the answer to question 2. What is the lead time, the elapsed time? By the way, just remember, lead time is just measured in time units, hours, minutes, seconds. Cycle time is a rate. That's different. So to the last question, what is the capacity of the system? Well, we know by now that the system's capacity will be defined by step number 2. And step number 2 can only process 1 loan every 20 minutes. That's right. So how many customers can we process within an hour? So if we can only process every 20 minutes, we can say that for an hour we can only deal with 3 loans per hour, or 3 customers loans per hour. So the complete system is subordinated to this bottleneck. The question was, how many loans can we process in 5 hours? Well, that is just multiplying 3 times 5 equals 15. As simple as that. 15 loans during 5 hours period. Okay, I hope you got that example. Let's just have another one. This is now a boutique. So that is called Barbara's Boutique. And here, once again, we have a flow chart that represents steps and decisions. This rhomboid, by the way, it represents, is an if. If that equals A, then it goes in this direction. If that equals B, it will go into that direction. So here's the description of the exercise. 2 types of customers enter Barbara's Boutique shop for customized dress alterations. After T1, which is the first step, type A, so that means this type of customer, proceeds to step 2 or T2. And then it can go to any of these stations, whatever is available. Eventually, number 4 And number 7, for sure, that's payment, because that's the common for customer A's, but also to customer B's, okay? The numbers in the parentheses are the minutes it takes that activity to process. So all these numbers that you see here are minutes per customer. Okay, so that's our process in a flow chart. So the questions are, what is the capacity per hour of type A customers? So just the segment, the upper segment of the flow. So what is the capacity? How many customers can we process? Number 2, if 30% of the customers are type A customers and 70 are type B, what is the average capacity? And here we have this word average. It's kind of an estimation. And number 3, when would type A customers experience waiting lines? That's WIP, so waiting, assuming they are not type B customers in the shop. Where, in which steps, would type B customers have to wait, assuming no type A customers exist? So we're going to look at the flow for type A and the flow for type B separately, and we're going to identify where they're going to wait, because remember, this is an unbalanced system. Every step needs different times, has a different rate. Okay, so we go for the upper part, that is type A, and that is everything you see here highlighted. So we're going to analyze this. We forget about this other part. Okay, so for type A customers, step 2 can process 60 divided by 13, because 60 minutes is an hour, 13 it takes per customer. So we can serve, this station can serve 4.62 customers an hour. This is how we measure it. Okay, step 3, which is these are 3 persons doing exactly the same job. Yeah, but they do have different times, maybe because of experience. Some people are faster than others. Okay, so this is how we're going to measure it. Step 3 has 3 workstations and a capacity of 60 divided by 14, so the capacity of A, plus the capacity of B, which is 60 divided by 10, plus the capacity of C isolated, which is 60 divided by 11. So we need to add, because this is running in parallel, step 3 is the same. So we have a lot of capacity here, and we can see that a lot of capacity reflected in this number is 15.7 customers per hour. Look, the contrast between step 2 and 3. Look how unbalanced they are. So you can already see that maybe we have too many people here, which we don't need, because this one is already restricting the flow. Okay, so step 4, same story, 60 minutes divided by 18 leads to 3.33 customers per hour. That is even slower. Yeah, so that is the slowest step. And lastly, there is step 7, that is the last at the end, but we can already identify that the bottleneck is located in step 4, because that is the slowest element in this whole chain. The fastest element is step 3. That's because you have 3 persons performing that job. But you know what? It doesn't really matter, because at the end, everything is restricted by this person. In fact, you can even omit 2 of these persons and still is the slowest step. Okay, so the speed of A is defined by 4, so we can only serve 3.33 customers per hour. That's it, of type A. Now let us analyze type B, and we just follow the same rationale. So step 6, in this case, you can clearly see is the slowest from the chain, and the way we measure it is 60 minutes divided by 22, because we only serve 1 customer every 22 minutes. That means during an hour we can serve up to less than 3 customers, 2.73 customers an hour. Okay, so now we have the capacity for type A, we have the capacity for type B. Okay, so assuming that we have 30%, that's 30% type A, and 70% type B, the whole system can run on average at 2.9 customers per hour, so a bit less than 3 customers per hour. Once again, have a closer look at this equation. We have a percentage for A, and that is its respective speed, and the percentage for B, 70, and that is its respective speed. So we are kind of averaging, kind of approximating the total system, the total Barbara's boutique capacity. We can say that is 2.9. Again, is average. I'm emphasizing that a lot because in real life you have fluctuations, sometimes a little bit more, sometimes a little bit less. So we always say average, 2.9 customers per hour. This is how we solve that. Now, where are type A customers waiting? Well, they always wait before the bottleneck, right? Okay, so every time we have a slow step, for example, that is very fast, and that is a bit slower than the previous. So the previous is 12 minutes per customer, and that's 13. So here, there will be some people waiting because this step is sending persons faster as this step can actually process them. So we have an imbalance here. We have a disparity. But the most drastic waiting line will occur obviously here because step 3, it has a capacity of 15.7 customers per hour, and this is just 3.3. So you have to imagine here, all the people are leaving, and they're all accumulating here more and more, and this is a growing waiting line, and this person is under a lot of stress. So this is an unbalanced system with very drastic workstations. Okay, what about for type B? Same story. We always look at the differences, and because step 5 is slower than step 1, that means that it cannot process at the speed that step 1 is sending them. So here we will have some waiting lines forming, but also here, because step 6 is very slow, so that is still faster and is sending people, and these people cannot be processed at that speed, and therefore we have a build-up here. So the answer is before steps 5 and 6 for the same reason. You see how it is? It's just like that picture of the papers in an office that I show you. It's exactly the same. That workstation, that desk is like a step 6 here. Okay. Lastly, we have another exercise. Now this time is about a car wash. Yeah, and that's Bill's Car Wash. Offers 2 types of washes, a standard and deluxe. The process flow for both types of customers is shown in the following chart, which is here. So here, maybe you pay in the beginning, maybe there's a pre-wash. It is the same for everybody, but then depending on what customers want, they will follow. If that is a standard, these steps, and if that is deluxe, they will follow these steps. Both wash types are first processed through steps A1 and A2. The standard wash then goes through steps 3 and 4, while the deluxe goes to A, 6, and 7. I think they just get wax or something fancy. And then at the end, they all get the same process of drying. Okay, so just like before, the numbers in the parentheses indicate minutes per car. Okay, so 4 questions. Number 1, which one is the bottleneck for the standard car wash process? So up here. Number 2, what is the capacity, which is measured as customer serves per hour, of Bill's Car Wash to process both a standard and deluxe? Assume that no customers are waiting at step A1, A2, or A8. So things here, there's no waiting, things are just flowing. What is the capacity? If 60% are going for a standard and 40 are going for deluxe, what is then the average capacity for the complete car wash? This is just like a similar question like Barbara's boutique. Okay. And lastly, number 4, where would you expect the standard wash customers to experience waiting lines, assuming that the new customers are always entering the shop and that no deluxe customers are in the shop? Okay. Where would the deluxe customers have to wait, assuming no standard customers? So just like Barbara's boutique, where do you expect here waiting lines, and where do you expect here waiting lines? That's WIP basically. All right, so let's go by parts. First, step 4 is the bottleneck for the standard. That's here, and that is obvious because it's the slowest. And here, that will be this 20. Have a look, 5 and 12 is still the slowest. So this is the slowest for standard, and that is the slowest for deluxe. These are the bottlenecks. The capacity for standard washes is 4 customers per hour. Why is that? Because this is the bottleneck, right? And every hour consists of 60 minutes. So if it takes 15 minutes to run through this complete process, 60 divided by 15 is 4. So we can only process 4 customers an hour because of A4. And this is the same logic we will also apply to deluxe. This is the slowest. It takes 20 minutes per car. So every hour we can only process 3 customers an hour, which is what we have here. 60 divided by 20. Okay, so quite simple. We have seen this before on the previous examples. Okay, so now what is with the waiting lines? Okay, so the standard wash customers would wait before the steps A1, A2, A3, and A4, because these activities that immediately precede them have a higher rate of output. So that means that that's faster than that. This is faster than that, that's faster than that. And that's not faster than that. So here it doesn't matter. So here we have a waiting line. So they will stop. Here they will be stopping. Here the same, and here the same, only here. Here we won't, because here's the opposite. You see, that is the slowest, the following step is faster. So here we don't have a waiting line. So what about with the looks? Same story, in front of steps A1, A2, because this is a common step, and A6, only here. That's too fast. A5 is just too fast for A6, but here we don't have an issue because that is faster, and customers are going at a very low rate. That is 3 every hour, and this A7 has a capacity way higher than 3 an hour. So here we don't have to worry, and we can also argue that no, here as well not. Here is faster. A8 is super fast. So that's also no whip, no waiting lines also here. So once again, every time that we have a system in which the following step is slower than the previous, then we have a chance for build up or for whip. That's a waiting line. Okay, so that's about it with these 3 examples. So constraints management is the management of bottlenecks, and we manage bottlenecks by first identifying where that is. And by identifying where that is, we can already determine the system's capacity. How many items per hour can this process serve? So wherever you want to improve, you want to do this exploit and elevation, it means that you have to go to these bottlenecks and find ways, sometimes by means of technologies, sometimes by means of redesigning a process or the activities, or sometimes by means of increasing the capacity at that stage, which is just adding an extra machine, adding an extra person, and then you can double, triple, and so on the capacity at that particular case. I hope you understood with this lesson the concept of bottlenecks, and that's it for now. Thanks a lot, and bye-bye.